Hello, this is Miss Moore, and today during chemistry we're going to discuss Lewis dot structures. Today's essential question: what is the point of Lewis dot structures and how are they drawn? So we'll start with what's the point of Lewis dot structures. So Lewis dot structures show how valence electrons are arranged among atoms in a molecule. And what Lewis dot structures do is they show the basic structure or organization of the molecule. And the reason we're caring about valence electrons is valence electrons are where the bonding occurs, and that in turn will lead to the basic structure of a molecule. And this is really, really important. The structure of a molecule will determine how it'll interact with other molecules. So it's important to understand molecular structure. The most important requirement for the formation of a stable compound is that the atom achieve noble gas electron configurations. And most noble gases have 8 valence electrons, which we call an octet. However, helium, the only noble gas that has 2 valence electrons, known as a duet. So, when you're drawing Lewis dot structures for molecules, what you want to do is try to satisfy the octet or duet rule for each atom if possible. Okay, drawing Lewis dot structures. So what we'll do here is we'll go through the rules or guidelines. Let's call it guidelines. We'll go through the guidelines for drawing Lewis dot structures, and we'll do a very simple example as we're going through those guidelines, and then we'll try some more difficult examples. Okay, here we go. So the very first thing you want to do is you want to write what we call the Lewis dot symbols for each of the atoms in the molecule. So how do we go about doing that? Well, let's say the molecule we're going to be talking about, we'll pick an easy one, CH4. So let's list the atoms that are in this molecule. Well, we have a carbon and 3 hydrogens. No, try again. How about 4 hydrogens? So now, what do I mean by the Lewis dot symbols? The Lewis dot symbols show the valence electrons for each of the atoms. And if you remember, valence electrons are the electrons in the outermost energy level. And the only sublevels that can end up with valence electrons are the S's and the P's. Okay, so we can have S, which has 1 orbital, and P, which has 3 orbitals. So together we could have a potential of 4 orbitals that can have valence electrons. So what we do is we have imaginary orbitals around the element symbol, and then we use dots instead of arrows and fill in those orbitals in the same manner we would for an orbital diagram, which means 1 electron in each orbital before going back and pairing them in. Okay, so let me get rid of this and we'll do this correctly. We don't usually actually draw the orbitals, we just draw them, they're just invisible. All right, so carbon has 4 valence electrons, and so that means 1 electron in each of the orbitals. Each hydrogen has 1 valence electron, so we'll stick those in. Okay, so those are the Lewis dot symbols for each of the atoms in the molecule. Okay, so now we need to arrange the atoms in the molecule, starting with the least electronegative atom, usually, or the one that needs the most electrons to satisfy the octet or duet rule, as the central atom. And then continue adding atoms, again, keeping that same order, the ones that need the most around the central atom. So let's put our example back. There we go. So now, of the carbon and the hydrogens, which one needs to most to satisfy the octet or the duet rule? Well, carbon needs 4, right? And each of the hydrogens need 1. So we will start with carbon. And now we need to arrange the other atoms around, in this case hydrogens, so that they can share the electrons, helping to get to the noble gas configuration for everybody. So let me start with one of the hydrogens. We'll take this guy. And if we stick them right there, then they can be sharing those 2 electrons, so they now pair up. I think I'm just going to draw the rest of the hydrogens. We can take, so we've used this guy. No, we haven't. We can take another hydrogen, stick him there, another hydrogen, and stick him there, and our last hydrogen goes here. So what we have now done is we've set this up so that now the carbon and the hydrogens are sharing electrons. So those 2 electrons go both for this hydrogen, who now follows the duet rule, as well as the carbon. And those 2 share, those 2 share, those 2 share. So now everybody is got a noble gas configuration. Each of the hydrogens have 2 electrons around them, following the duet rule, and the carbon now has 8. So everybody is happy. Okay, a point we're not going to practice right now, but we will get to later, is that often the formula is written in the bonding order. Okay, so keep that in mind, and we'll practice that in a few minutes. All right, so the next thing we need to do, make sure we do, is we need to sum the valence electrons of all the atoms in the molecule. So let me put our figure back, and it's kind of in the way, but hopefully we can see this. How many electrons did we have? We had 2, 4, 6, 8. All right, so we started with a total of 8 electrons. And truthfully, I would say that doing step 2, and that should actually be step 3, I would do step 3 while I'm writing the Lewis dot symbols for each of the atoms. So know how many electrons you're starting with. Okay. And another point that we will practice later is that if the molecule is a polyatomic ion, so example of a polyatomic ion would be CO3 2 minus. Make sure that when you're doing this count of how many valence electrons, that you account for the lost or gained electrons in your polyatomic ion. So this is 2 minus, which means when we do the valence electrons here, we want to also add up 2 more electrons. All right, now what we're going to do is connect the unpaired electrons between atoms to form bonds. So let's put our structure back. So instead of having these dots are showing that the atoms are sharing these electrons, so we turn them into lines. And normally you would rewrite them, so you would end up with something like H, C, H, H, H. And each single line represents 2 electrons. Okay, now make sure that each atom has a duet for hydrogen or an octet of electrons. So again, remember, those lines represent 2 electrons. So this hydrogen has 2 electrons. He's good. Hydrogen has 2 electrons. He's good. Hydrogen has 2 electrons. He's good. And hydrogen has 2 electrons. He's good. Now, looking at the carbon, so these lines also represent, the electrons for carbon. So we have 2, 4, 6, 8. So carbon has 8 electrons. So he's good. So everybody now in the molecule follows the octet or duet rule, has noble gas configuration. And the last step is to count the total number of electrons you have to make sure that you have the same number of electrons you started with. And I've got a complete mess here. But each line represents 2 electrons. We have 4 lines, which means we have a total of 8 electrons, which is how many we started with. So we did it. Okay, so there's a very easy example showing how to draw Lewis dot structures with the general guidelines, and now we'll try some that are more difficult. All right, let's draw the Lewis dot structure for HCN. So what was the first step? First step is to write the Lewis dot symbol for each of the atoms in the molecule. So H has 1 valence electron. C has 4 valence electrons. And last we have N, which has 5 valence electrons. Now we need to start with the least electronegative, or the one that needs the most, and that would be carbon. So let's start, whoops, carbon is white. Try that again. Start with carbon. And we need to hook carbon up with one of the 2 that are left. Hydrogen only needs 1 more electron to be like a noble gas, and nitrogen needs 3. So we'll go with nitrogen next. And they can share these 2 electrons. Okay, don't worry about any of the other ones yet, just go with that. And last we have hydrogen. Now to decide where to put hydrogen, because there's spaces for hydrogen on both the carbon and the nitrogen. So how do you know where to put it? Start by trying to put the hydrogen to the one that needs the most. And nitrogen only needs 2 more, carbon needs 3 more, so we will put the hydrogen here. All right, so far so good. The problem is we've made neither carbon nor nitrogen happy. You will note that carbon has 2 more spots for bonding, as does nitrogen. So what can we do? Well, we can form multiple bonds. So let's try that. So the first thing I'm going to do is I'm going to rearrange a little bit on nitrogen. I'm going to move this electron and put it here. It doesn't really matter as long as you have the same number of electrons. Okay, so now what we can do is carbon and nitrogen can share those electrons and those electrons. And I forgot a step, which was to count how many electrons we had to start with. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we started with the total number of electrons, 10. Okay, so now let's redraw our structure, and but use lines wherever there are dots. So we have hydrogen, carbon, and what I'm going to do here, there's those 3 lines, but I'm going to take those 3 lines, squish them together to make it look a little neater. So that's a triple bond there, right? And nitrogen. Okay, so is everybody happy? Let's check that. Hydrogen has how many electrons around him? 2. How about carbon? Each line represents 2 electrons, so he has 8. And nitrogen, 2, 4, 6, and the pair makes 8. So everybody's happy. Everybody has noble gas configuration. So the last step, how many electrons do we have ending up? We have 2, 4, 6, 8, and 9, and 10. So we have 10 electrons, which is how many we started with. So we did it. All right, let's try another one. How about CH3COOH, which is acetic acid. Now, this one, let me go back to a point real quick. Okay, point 2a says often the formula is written in the bonding order. And that is actually the case for the example we have right now. You will note that we've got the C's written twice and the H's written twice and the O's written twice. What it's showing is that it's basically going to be bonding in that basic order. So let's try this. Start by writing out all the atoms. We have C, and we've done this several times now, so we know it has 4 valence electrons. We have 3 H's, which each have 1 valence electron. We have another C, and 2 O's and an H. And the oxygens have 6 valence electrons, so we have 1, 2, 3, 4, and then we're going to pair electrons up, 5, 6. And same with this one. By the way, I don't think I made this clear. The bonding electrons are the ones that are not paired. So for the oxygen, these 2 would be bonding electrons. Those would not bond. All right. So we know that the basic bonding order is going to be C and H's, and then C, and then O, and then O, and then H, something like that. So we still want to start with the most electronegative, but keeping in mind the bonding order. So I'm going to put a C here, and I'm using that first C. Then we have H's. Now, H's can only bond one time. So we know that the H's are not going to be bonding with both C's. So I'm going to take these 3 H's here and place them around the carbons like that. So now we're at the next C, which is probably going to go right next door here. All right. All right, then we have O, O, and H. So this one might take a little bit of thought. We know an O and an H are going to go together, right? So let me draw that out. So I've used those, although they do need to be connected. And then we have this H here. So the question is, should that O, should the O go like that? If you look at it like that, that doesn't look like it's going to work because the C, everybody's got a stable octet except for the C here. So what I'm going to do is get rid of that. I'm thinking that this O, guess I should just get rid of the O too, is going to bond with the carbon like that, and then this O this O here, this OH, I can do this really. All right, let's just redraw. So this O can go here. Like that. Let's connect some lines and see where we're at. So we've made almost everybody happy except that carbon. Oh, nope, and the oxygen. You will note that there's a bonding spot there and there. So how about if I take this H and put him here, and I'll move this electron, pair it up there. Now they can bond. And once again, I forgot to count the number of electrons, so let's do that real quick. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 electrons. And let's check our structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. All right, so we're good to go with that. It looks like everybody has a noble gas configuration. So the last step is just to redraw this mess and make it look a little neater. So we have H connected to a C, H connected to a C, and then we have a double bond O with some paired electrons, and we have an O with some paired electrons connected to an H. So, sorry, it doesn't quite fit there. So there you go. In this case, again, the formula kind of told us the order, right? We've got, if you look, we have CH3, CO, COOH, COOH. All right, let's try one more, this time with a polyatomic ion. All right, let's use CO3 2 minus, or carbonate. All right, so let's draw the Lewis dot symbols. And we've used all of these atoms before, so we know what they're going to look like. All right, and this time I'm going to remember, let's count our total number of electrons. So we have 4, right, and 6, and 6, and 6, which gives us 22 electrons, plus we have a 2 minus there, which means somewhere in there there's going to be another 2 electrons. Don't worry about putting them in yet, which gives us a total of 24 electrons to work with. Okay, now do what we've been doing. Start with the one that needs the most electrons, which would be our carbon. And now let's stick in the other ones. So we'll put in oxygen. I'm going to put him here. Doesn't really matter. So we'll connect those. Now, where am I going to put the next oxygen? Carbon has 3 more bonding spots. Oxygen only 1. So let's put that oxygen again with the carbon. And 1 more oxygen. Where should we put this oxygen? Well, I would say let's put this oxygen again with the carbon because he still needs 2 bonding spots and the oxygens each need 1. So, got that. So we've now used all the atoms, but if you note, we still have 1, 2, 3, 4 more bonding spots. Well, we could form a double bond between the carbon and one of the oxygens. So I will move this electron here, that can bond there. So now the carbon, this carbon is happy and this oxygen is happy, right? Noble gas configuration, but not the other 2 oxygens. However, remember we had these 2 extra electrons. So I can stick one there and there. Now everybody has noble gas configuration. We have 22 plus 2 electrons. So we've done it. Now let's redraw this mess. Oh, the only thing you have to do when you do this is you need to show that this is a 2 minus. So now we're going to have something like that. And this whole thing has a 2 minus charge. All right, there you go. That's it for today. Have a good one.